Welcome back, chemistry fans. Now we are going to work on our Unit 13, Topic 4. Some stuff that is going to it's going to get into some heavy acid and base stuff, something called the Ka value. So let's jump right into it. Let me share my screen with you and we will get started. Okay, so I sort of misspoke there. We're actually talking about titration, but let's get into it anyway. So here we go, sharing my screen with you. And now we're going to talk about the lab that we just performed in the class and how we can utilize that data to make some calculations. So titration is a process whereby you take a burette and you can get exact measurements of how much of one of the unknown materials, of the known material. So this could be an acid and base. Usually the base is what we start with up top and we deliver it into the acid down below so that we can see this color change occur. It's not always the case, but it's normally how we would work it. So the acid would be down in the flask before, and you keep adding one into the other until you hit either the neutralization point where you identify with a pH probe or with some color change indicator. Okay, so as you're seeing here, this is the process again. You add to the flask the acid, you add an indicator so it changes color, and then you fill up the other material in the burette. You start adding that material to the flask. It fills up, and as it fills up, it might change colors. You stop, and you get your final reading. So then you know the concentration of the known in the burette with the amount. You now have the amount of acid or the known in the flask, but what we don't know and what we're going to calculate is the concentration of that unknown material in there. So a reminder of what's happening in these titration reactions is that you will see you would see these neutralization reactions. A neutralization is just a acid and a base being added together. They form water, and that's where the pH is equal to 7. And that's usually the goal of our titration, is to reach that point. What this is going to look like, and this is the second lab that we're going to do, is we're going to try and create this graph here, this typical S point curve, where you see the pH is equal at 7, and it has these top and bottom points where the pH was low to start off with, where we didn't have any base in it, and then we kept adding it, and it goes up high. And this time we're going to try and make it go slower than what it did the last time. Now, that's if we have a strong acid and a strong base. And that's what you see up here in the right-hand corner. Now, what happens if we don't use strong acid, strong base? Well, one of them is going to overpower the other one. So with a strong base, what you will notice is that the equivalence point is higher than 7. And it's just the opposite. If we use a strong acid, we'll see the pH go lower. And I think that that starts to make sense. They overpower it because there's more of those particles in there, and the weak acid or the weak base, it takes more material to overpower them and find that equivalence point. Now, what if we use a weak acid and weak base? You'll see that the line starts to just kind of lay down. It doesn't quite have that distinct area that we like where we can find our equivalence point. It's a little more hidden in here somewhere that we would find that equivalence point. But a weak acid, weak base, its pH will also be somewhere right around 7. All right, now what if we have a material that has more than one H in it? So in other words, if I were to use H2SO4, it will not release its H's simultaneously. So what, or actually, let's use some, because that is a strong acid and it will. Let's use carbonic acid. What happens is it will release one of its hydrogens, and then it will release the second hydrogen separately. And that's what is being represented with these two areas where I have two regions on the titration curve where it's going up. So you have to be able to recognize that those different plateaus mean that it is got more than one H. And if it had 3 H's, well, then it would have 3 plateaus that we could find the equivalence point. All right, so let's go ahead then and do some calculations with the titration curve and trying to solve for one of the unknowns. Our formula that we have done, oh, let's see if this, hold on. Let's see here if we have any data here. No, so we don't. So we need this formula right here. So the formula that we are looking for is M1V1 equals M2V2. Well, we ran into that same exact equation when we were dealing with solutions. The ones and the twos were initial and final volumes, how they changed. Well, what we're going to do today is we're going to work with similar idea, but instead we're going to work with acids and bases. Now, this formula works if we have strong acids and bases. If we have weak, then what happens is those acids, those H's are going to be given off at different times. So we will need to count how many H's there are and how many OH's there are. If it is a weak acid, if it's a strong acid, they will dissociate entirely separately from one another. Okay, so let's go back to the questions now and let's see if we can calculate what we've got. Our acids are together, so I've got 25 milliliters of 0.2. And I have 0.1 of the molarity, but I don't know what the volume is for that base. So let's do the math and let's divide both sides by 0.1. And so we'll end up with the volume by itself. So I've got 25 times 0.2 divided by 0.1, and I get 50 milliliters is what I'm going to need to calculate. Let's do the same thing for the next one. Now notice this is still a strong base, so that's okay. So both of those H's are going to be released at the same time. So what that's going to mean is that I am going to need to multiply by the number of H's because it's going to release both of them at the same time. So I've got 175 milliliters times 2 because there are 2 H's. And I'm going to set that equal to first I've got to multiply it by the molarity of the base, but what I'm going to set that equal to is 125 times 8.5, the molarity of the base. Now I don't need to multiply that by 2 because there's only one OH. So I solve for my MA. I've got 125 times 8.5 divided by 2 divided by 175, and I end up with 3.03 will be the molarity of the acid. And I believe the next two problems are the exact same. So we're fine. We don't need to do any more practice. I think we're good with this. Thank you very much for paying attention. I will talk with you again soon. Bye-bye.